So we've talked about two different ways to represent vectors in 3D. We've talked about Cartesian. We've talked about coordinate direction angles, also called direction cosines. And we'll come back to another example of this here in a moment. But let's go to another example. So another way that we express vectors in 3D, I call spherical coordinates. If you look at official spherical coordinates, so you have a vector here. This is x, this is y, and this is z. The projection of this vector onto the xy plane looks like this. And the angle from the x-axis to this projection is a positive theta. If I had to go the other way, this would be a negative theta. And then you have an angle upward from the plane, which I'll call phi, or you have an angle downward from z, which we would call psi. And you might say, well, when did this arise? And then, of course, you have a force magnitude. And so in spherical coordinates, you'd basically say an F vector is equal to an F magnitude, angle theta, angle psi. So positive psi is down from the positive z-axis. Again, this seems kind of theoretical to you, but it's actually a real practical problem because this angle theta is called an azimuth. If you take a surveying class, which many of you did, or many of you will, basically an angle measured in the plane is an azimuth. In surveying, you basically take north as 0 and you go clockwise 0 to 360. So east is 90, south is 180, and so on. So an azimuth is measured in the plane. In statics, we'll measure the azimuth basically from the x-axis. So that's an azimuth. And then elevation is like this angle. And so if you think of a satellite dish, it looks something like this. Its direction as it rotates it or horizontal in the horizontal plane, that's its azimuth. And then basically as it moves up and down, then that's its elevation angle. It's phi. So it's a pretty common, if you're pointing a Starlink satellite dish, you're going to point it in the correct direction, which is the azimuth, and then the correct angle this way, which is the elevation. Anyway, if you're in the Army and you're firing a howitzer or some other artillery piece, again, you've got an azimuth and you have an elevation angle. And so this is actually pretty common. The question is, how do I deal with this in statics? And we're going to look at some examples here in a moment. But let's say this theta is 50 degrees, measured from the positive x. Let's say that this phi is 45 degrees. Well, let's do it differently. Let's say it's 40 degrees, up from the xy plane. And let's say F is equal to 100 pounds. There's two ways you can deal with that vector. The easiest way is to put it directly into your calculator. So this is your calculator format. This is one of the reasons why I strongly recommend that you get a TI-89, which I think is discontinued, but get a used one or get an nSpire, because it allows you to enter spherical coordinates directly if you're given a problem in spherical coordinates. And so for this particular problem where F is 100, theta is 50, and phi is 40 degrees from the axis, then I want psi, which is this angle here. So if this is 40, then psi is 50. And so I'm basically going to put in, we're going to go control square bracket. We're going to go 100, comma. I need the angle symbol. So I'm going to go control symbol, and there's my angle. And now enter my theta, which is 50. And then I go comma. Then I need control, angle symbol again, enter. And now I'm going to enter 50 here. And again, which is the angle from the positive z. And I'll go 50. And that'll be enter. And so my calculator is in its default display mode is rectangular. So I entered the vector the way it was given in spherical coordinates, but it automatically displayed it in Cartesian. So it comes up as 49.2, 49.2i, 58.7j, and 64.3 k pounds. That's my F vector. So if you've got a calculator that's capable of it, I strongly urge you to do it that way. If you have more of a basic scientific calculator, then you have to do this as a two-step process. So what you have to do is find an F projection, and then find this FZ. The FC is easy. So if this is 40 degrees and this is 100, the FC is basically this guy here. So FZ is 100 sine of 40. So FZ is equal to 100 sine 40. If you put that into your calculator, so 100 times sine 40, enter, you get 64.3. 64.3 pounds, which is what we got there. So that's FC. So what we're looking for is ultimately is FX and FY. So once we get the projection, we can take, and if we know this angle is 50 degrees, then Fx is the projection times cosine 50. Oh, we need a projection. Okay, so the F projection, so F projection is equal to F cosine of phi, or you can call it F sine of psi. Either way. So F is 100 cosine of 40. So my F projection, 100 times trig cosine 40 is 76.6. That's my F projection. But now to get the Fx, I have to project the projection. So I have to project the projection onto the x-axis. And so basically Fx is equal to 76.6 times the cosine of theta, which is 50, times cosine of 50. And so 76.76 times cosine of 50 I get 49.2. 49.2 pounds, which is what we got here. And then finally, Fy is equal to, I'm sorry, I'm probably running out of real estate here. Let's move this up. And so Fy, if this is 50, then I can go Fy is equal to F projection times sine of 50. So this is 76.6 sine of 50. And 76.6 times sine 50 is 58.7. 58.7 pounds, which is that. So if you're given a vector in what I call spherical coordinates, the easiest way by far is to know how to use your calculator and enter it directly into your calculator. And we'll work a number more examples of this. However, you also need to know the harder way of doing it. And the harder way is to Fz is F times the sine of this angle. Fx is F times cosine of this angle times cosine of this angle. And Fy is equal to F times cosine of this angle times sine of this angle. And that's basically what I give. I think I give that to you here. So when you look at these official formulas, if you've got a positive theta from the positive x, we have a positive phi here, then fx, which wasn't listed here, but if we put fx here, this is fx, fx, and this is fy, and this is fz. So fx is f sine of phi, which is the f projection, times cosine of theta, which gives you fx. Fy is f sine of phi, which is the projection, times the sine of theta, which gives you the y. And then finally, fz is equal to f times cosine of phi. So you need to be able to do both ways. You need to be able to recognize it, and you need to be able to enter it into your calculator, which I vastly recommend, or be able to find f projection and find fx and fy. It should be easy for you to do. The fourth way of representing a vector in 3D is a force along a line, but we'll work some examples of this later. And so I'll just mention it now. You basically write a unit vector you write a line vector along this line, and then you find the unit vector of that line, and then you have a force magnitude, which you multiply times that unit vector. And so that's the fourth way of representing vectors in 3D. Cartesian, coordinate direction angles, also called direction cosines, spherical coordinates, force along a line. You need to be able to do all four and go back and forth between them.